Hello, my name is William Oliver. I'm the Henry Ellis Warren Professor of Electrical Engineering and Computer Science and Physics at the Massachusetts Institute of Technology. And today I'd like to present on an introduction to quantum computing, qubits, gates, and algorithms. Before we get into quantum computing, I think it's worthwhile to take a look back at the history of classical electronic computing. Back in 1906, the vacuum tube was invented. It's a three-terminal device, and for many years it was used in radio transceivers before it found its use in computing in a computer called ENIAC, developed at the University of Pennsylvania in 1946. You can see that this computer takes up, the better part of a room. This is a man here working on it. The following year, the transistor was invented at Bell Laboratories, and within about 10 years, we had our first fully transistor-based computer called TX0 or TIXO, developed here at MIT and Lincoln Laboratory. And again, you can see this computer takes up, the better part of a room. Now, it was fully transistor-based, but basically it was taking transistors and soldering them together. And in fact, it used a magnetic core memory, not based on transistors. To get closer to the computers we're using today, we would first need the integrated circuit developed in the late 50s, but it was still a good 15, 20 years before we had the types of integrated circuits that we would recognize, such as the one shown here. This is the Intel 4004. It's a 4-bit processor with about 2,000 transistors. You'd have to fast forward to the mid-90s to get chips like the Pentium Pro with millions of transistors. And again, another 25 years to get to where we are today with multi-core processors with billions and billions of transistors and graphical processing units. Today, the transistor count approaching even 100 billion transistors on a single chip. And looking back from this vantage point, it's well over 100 years of development from the first logic element to the chips that we have and use today. Now, we can compare with that quantum computing, which is much more recent. In the early 1980s, Richard Feynman here at MIT at a meeting at the Endicott House suggested that if you want to simulate or emulate a quantum system, we should use a second quantum system to do that. And basically, he was proposing quantum computation. Now, people thought about, what that means and how we would even use a quantum computer. And by the mid-1990s, 15 years later, we started to see the first theoretical proposals for quantum algorithms, such as Shor's factoring algorithm, which we know attacks RSA crypto systems, or Grover's algorithm for unsorted database searching. And we even saw the first proposals for quantum versions of error correction, which would allow us to operate quantum computers for longer periods of time, even though the individual components, the qubits themselves, could be relatively faulty. In the late 1990s, we saw ideas for quantum annealing, adiabatic quantum computing. And by the early 2000s, we had the first demonstration, in fact, of Shor's algorithm, which is a factoring algorithm on nuclear magnetic resonance, or NMR, liquid state systems, factoring 15 into the numbers 3 times 5. Okay, trivial problem, but it shows that Shor's algorithm can work if we and when we can build quantum systems that are large enough, quantum computers at scale. You'd still have to advance 20 years to get to where we are today, where we now have few qubit processors, 50, 100 qubits, available in the cloud that people can use from IBM, and also demonstrations of quantum advantage, in this case by Google, on a 53-qubit quantum computer. So what's the takeaway? The message is that, look, quantum computing's real. It's transitioning from scientific curiosity to technical reality. That's happening around us right now. But as engineers, we also know that advancing from fundamental discovery or first logic devices to useful machines is going to take time and certainly a substantial amount of engineering. Another takeaway that I see is that you need to be in the game to play. And what I mean by that is that it may not be a big surprise that many of the companies that are making these chips that we have today with billions of transistors didn't just jump in the field late. They were in it and its development for decades. So with that, let me present an outline. I'd like to talk about an introduction to quantum computing, I'll then talk about superconducting qubits, engineering quantum systems, and 3D integration. So first off, how is a quantum computer different than a classical computer? Well, let's begin with classical computers. We know that they're built from logic elements that are called bits or classical bits. Now that could be a transistor, voltage on a transistor, could be spin in a magnetic memory, but the one we commonly use, of course, is transistor. And the states are 0 or 1. The valve is on or off. These are discrete states, and the transistors are really, really good. There's almost never an error. The error rate for a transistor today is maybe 1 part in 10 to the 20th power. So basically, these states are deterministic. If you set it in logic state 1, you'll measure it in logic state 1. Set it in 0, you'll measure it in 0. Quantum computers are different. They're based on a quantum version or quantum mechanical bit that we call a qubit. And it can be any coherent two-level system. And the way that we think about it is on something called the Bloch sphere, or think of it as the planet Earth, where the North Pole will assign state 0, and the South Pole will assign state 1. And if you're at the North or the South Pole, basically you're a classical bit, just like the transistor. But of course, we know that we can be anywhere on the surface of the planet Earth. And when we're anywhere other than the North or South Pole, we are in a quantum superposition state of 0 and 1 simultaneously. And we write it like this. This funny bracket notation represents a quantum state 0, quantum state 1, with relative weighting coefficients alpha and beta, which in principle can be complex numbers. But the point is that this is a single state, just like you're at a single place on Earth. But it has aspects of both 0 and 1 simultaneously. And we can equivalently write this using vectors in a linear algebraic notation, 1, 0, 0, 1, corresponding to logic state 0, logic state 1. So these are quantum mechanical superposition states, manifestly quantum mechanical. And one consequence is that if you go to measure this state, the measurement results in a classical result, but it's probabilistic. So for example, if you're on the equator where the magnitude of alpha equals the magnitude of beta, then 50% of the time you're going to measure a 0, and 50% of the time you're going to measure a 1. It's the purest form of randomness that we know of today. And so what this means is that quantum computers rely on encoding information in a fundamentally different way than classical computers. And this has, of course, consequences. So one way to look at the consequence and then ultimately the power of a quantum computer is to think of, again, a classical computer and the bit. And if we have n bits or n transistors, we can form an exponentially large number of states, but we can only represent one n-bit state at a time. So if n is equal to 3 transistors, we can form 2 to the third power, or 8 different states, represented by 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. But we can only represent one of them at a time. And so if we want to, say, for example, calculate the outputs for all of these inputs, we basically have one of two options. First of all, we could take one computer, input and input, 0, 0, 0, calculate the output, and then on that same computer, serially in time, keep putting in new inputs and get new outputs. Alternatively, we could buy 8 different computers and in parallel, at the same time, feed in a unique state into each one and get the output. Either way, with an exponentially large number of states for n bits, we would need either exponential time or exponential hardware. Now, on a quantum computer, we again can have n qubits, which again have 2 to the n different components or aspects, but we can put all of them into a single superposition state, one state that carries all of these aspects from 0, 0, 0 all the way up to 1, 1, 1 with a different complex weighting coefficient for each one. And the consequence of this is that we can get a quantum version of parallelism and, importantly, interference. And figuratively, what we do is we take this single quantum superposition state, with all aspects, an exponential number of them, put them into the quantum computer, and then the quantum computer will spit out another superposition state. And we'll see what happens at measurement in just a moment. But as we can see, this is a very different way of processing a large amount of information. So the question is, how do we take advantage of this quantum information? Well, let's think about, again, classical versus quantum bits. And we can do that in the context of spins. These can be classical or quantum. So we've got 3 atoms. Let's say each one has an electron spin. We remember that if we put the spin in a magnetic field, that we'll get the Zeeman splitting. So one of these spins is at a higher energy than the other one. We'll say the spin down versus the spin up. And we'll associate that spin up with state 0 and spin down with state 1. Now, as we said, we can form 2 to the n unique states with this classically. So that's 2 to the third, or 8 states. And we can even write them in a state register shown here, from up, up, up to all spins down, down, down. And if we associate the number with them, that's 0, 0, 0 down to 1, 1. Okay, this is all classical at this point. Now, equivalently, we can write a single quantum mechanical state that comprises all of these aspects at the same time with weighting coefficients C1 through C8. We can look more digital by replacing spin up and spin down with the zeros and ones like this. And again, I want to emphasize that these are in principle complex numbers, and we need 2 to the n, or 8 of them in this case, to represent our single quantum mechanical state. And I'll keep harping on the fact that there's a single state that has 8 aspects. So we can think of this state space now as a quantum state space where each of these aspects that make up our single quantum state have a weighting coefficient C1 through C8. Okay. So now let's take a look at pictorially what we mean by quantum parallelism and quantum interference, which are realized by this quantum superposition state and quantum gates. Okay, so the first one we're going to think of is, we'll give an example of quantum parallelism. And to do that, we're going to consider a quantum operation, which we'll look at again in more detail in just a moment. But here, let me just tell you how it works. This is called a pi pulse. It's an electromagnetic pulse, the frequency of which, the fundamental, is resonant with this transition. And it has the right amplitude and duration to do a 180-degree rotation. Okay, what do we mean by that? So if the qubit is pointed towards the North Pole, let's say, then what this pulse will do is it flips the spin from up to down, which we represent on the block sphere for the planet Earth is going from the North to the South Pole. And that's a rotation of 180 degrees, which is why we call it a pi pulse. Okay. Now, had the qubit been in the down state, then it rotates that spin to the up state. Okay, so pi pulse. And what we're going to do is we're going to see that this shuttles coefficients between different states. Now, we apply this pulse only to atom 1, or to the spin 1. Okay. And we can look at our quantum register before and after the pulse. So let's take a look at the case where, or all of the aspects that are spin up. So again, we're applying one pulse to only qubit 1, or atom 1, and 4 of the 8 aspects have spin up. So those 4 will be flipped to spin down, and the coefficients C1 through C4 will follow along. Okay, so basically it's that aspect now just flipped, but of course it still has the weighting coefficients C1 through C4. Now, instead, for the aspects where it was spin down, well, this pi pulse is going to flip that to spin up. And of course, the coefficients C5 through C8 follow along. So what we see is that we've applied one pulse to one atom, one qubit, one spin, but we've basically operated and shuttled 2 to the n coefficients simultaneously, right? So one pulse, one atom, but we've changed 2 to the n coefficients, in this case, 8 coefficients. So we've operated on the entire system simultaneously. This is quantum parallelism. Okay. Now, we can further look at an example of quantum interference in the following way. So we have an electromagnetic pulse. It now has half of the amplitude, it turns out. So that's going to do a pi over 2 pulse. And the way that this works, we'll see before and after. So if we have a case where it's a spin up, then that spin up is going to rotate down pi over 2, which takes it to the equator. And I'm just going to assign this direction as a plus sign for simplicity. Now, for experts, we know that this is a superposition state and it requires a normalization factor of 1 over square root of 2. We're not going to worry about that here because we just want to look at the interference aspects of it. So spin up goes to up plus down, the plus sign coming from this direction. And let's take a look at, we're applying this pulse now to atom 3. So we'll just look at this particular case where we have a spin up for aspect that has a coefficient C5. And by rotating pi over 2, we're now going to associate that with both an up and a down, up plus down. And the coefficient C5 follows with that plus sign. Now, again, there's a normalization that I'm ignoring here, but that's okay for this purpose. Now, similarly, if the spin had instead been spin down and we rotate in the same direction by pi over 2, we're now again on the equator, but pointed in the opposite direction. And so that will come in with a minus sign because it's opposite of the plus sign. So spin down, we'll say, goes to up minus down. And so where we had a downspin here with coefficient C6, that now is associated with the up and down with now a minus sign that is associated with the down component, right? So we have C5 plus C6 and C5 minus C6. And so what we see is that if C5 equaled C6, doesn't necessarily need to be so, but if it did, then what we would see is that the weighting coefficient on up, up, up doubles, and the weighting coefficient on this spin down part completely destructively interferes and in fact equals 0. This is an example of quantum interference in a digital computational case. Now, we also see that this is an example of quantum parallelism because it happens across the entire quantum state space at the same time. So again, we've applied one pulse to one qubit, but we've impacted all 2 to the n coefficients, both through quantum interference and through quantum parallelism. Okay. So we have quantum gates, and they have an analog, right? In classical Boolean logical computing, we have Boolean logic gates, and I list them all, well, not all of them, many of them here, the NOT gate, the AND gate, OR gate, etc. And the truth tables are here. They're input states to output states, what these gates do. And I've blown it up here. So the NOT gate takes 0 to 1, 1 to 0. The AND gate, you can see its truth table, the OR gate, its truth table. And the point is that we can form a universal set of Boolean logic gates by taking just a handful of these options here. And it's not unique. So for example, the NOT gate and the AND gate together form a universal set. The NOT gate and the OR gate, or equivalently the NOR gate, that is a universal set. And what we mean by universal is that from any state in the state space, any starting point, we can get from any state, let's call it A, to any point B in the state space using just these gates. Now, depending on the starting and ending point, some set of gates may be more efficient than others, but it's possible with a universal set of gates to get from any point A in the state space to any point B. And we'll just note that this requires at least one 2-bit gate to do it. Okay, now quantum mechanically, it's a similar story. We have a set of single qubit gates. These are gates that operate on a single qubit. We give them names like identity, which we don't do anything. X is a rotation around the x-axis of 180 degrees. Y is a rotation around the y-axis of 180 degrees. And other ones, Z, S, T, H, etc. Now, there's just a small handful of these gates. And we represent them linear algebraically in the following way with a matrix. The identity clearly is the identity matrix. The X gate, the Y gate shown here. And we also need 2 qubit gates. And the 2 qubit gates that we'll look at, controlled NOT or controlled phase to give examples, are cases where the state of one qubit determines what happens to the other qubit. And they have a truth table like this. And we'll see an example in just a moment. But the point again is that with just a handful of these single and at least one 2-qubit gate, we can form a universal gate set for quantum logic. And so here's one example here. Again, it's not unique, just like with classical gates, it's not a unique set, but it does have the property that you can get from any point A in the quantum state space to any point B in the quantum state space with this universal set. There's another property of quantum gates, which is in fact, unlike classical gates, quantum gates are fully reversible. There are some example of Boolean logic gates which are reversible, but quantum gates must be reversible. And again, it requires at least one 2-qubit gate, which we call an entangling gate. Okay. So let's see a couple examples of these quantum gates. And the single qubit operation that we're going to look at has an analog called the classical NOT gate that takes 0 to 1 or 1 to 0. And the quantum version of this NOT gate is an X gate, which takes quantum state 0 to quantum state 1 or vice versa. This is what it looks like in simulation. So we've got our block sphere. The block vector, or the qubit, starts at the North Pole and is rotated to the South Pole by an electromagnetic field that we apply along the x-axis. And that's why it's called an X gate. Now, we'll talk in a moment how we actually do this. But just for a moment, let's imagine that we can electromagnetically do this. And what you see is the envelope of our pulse, and it looks Gaussian, right? And it's applied along the x-axis, or as we'll find out, in phase. Now, the way this is here, it just takes 0 to 1, which, as I mentioned, it's North Pole to South Pole, and that's just a classical starting point, a classical ending point. But the point is that we need not start at the North or South Pole. We could start anywhere on the surface of the planet Earth, which represents a superposition state. We start in a superposition state, and we end in a superposition state by rotating 180 degrees around the x-axis. And what this X gate does is it takes and swaps the coefficients on the 0 and 1. You can see here that alpha 0 plus beta 1 goes to beta 0 plus alpha 1. Okay, that's an example of a single qubit gate called the X gate. Now, a 2-qubit controlled NOT gate has an analog that's classical, and that's the classical exclusive OR gate, or XOR gate. One way to look at the classical gate, as you may remember, is you have 2 bits, one X, one Y, and we'll say the X bit is a control bit and Y is a target bit. And if we look at the input and output truth table, when the control bit is 0, we just pass the value of the Y bit to the output, the 0 and 1. But when the control bit is 1, we invert the Y bit and pass that to the output. So 0 becomes 1 and 1 becomes 0. It's the same story with the quantum C-NOT gate, only we're using qubits now, X and Y. One is a control qubit, one is a target qubit, and this is the symbol for the controlled NOT. So it's a controlled NOT, target qubit. The dot here means the control qubit. And the truth table looks similar, just with quantum notation. And when the control qubit X is 0, we pass the state of qubit Y to the output. And when the control qubit is 1, we invert, do an X gate, right? We'll take qubit value 0 to qubit value 1 and 1 to 0. So the rotation of the target qubit Y depends on the state of the control qubit X. And this has some very interesting consequences. So for example, if we take a state where the control qubit X is in a superposition of 0 and 1, and the control qubit Y is in state 0, we get some interesting results. So we can take it one by one. The rules of linear algebra apply here. So when the control qubit is in 0, right, the target qubit is just passed to the output. So Y stays the same, stays in a 0, with X being in its 0 state. Plus, when the control qubit is in state 1, we know we need to invert the Y qubit, so 0 becomes 1 here. And now what we see is something very interesting. This turns out to be an entangled state. It cannot be factored any longer into only an X component and only a Y component. You can see that they're fundamentally correlated here. Turns out that this is true in any basis, not just in the Z basis that we're showing here, but if we convert it to the X basis or the Y basis, it would still be entangled. And this is why the 2-qubit controlled NOT gate is called an entangling gate. So a universal set of gates, or gate-based quantum computing, is achievable with just a small set of single and 2-qubit gates of the type that we've shown here. You can do any quantum logic this way. So with that, we can run a quantum algorithm. And what an algorithm looks like is, figuratively or pictorially, the following. We start with a qubit in a equal superposition state. So no normalization here again, but we have aspects 0, 0, 0, 0, 0, 1, all the way, et cetera, all the way out to 2 to the n. In this case, it's just 3, so it would be 8, but you could have n qubits and you would have 2 to the n such aspects. And we prepare it in an equal superposition state. So all of these have an equal weighting factor. Again, I'm not worried about normalization here. And what an algorithm is just a sequence or series of single and 2-qubit operations. Some of them can be run in parallel, but let's imagine here that we have a single qubit operation that operates on the 3rd qubit. So again, a single operation on 1 qubit, qubit number 3, but we see that with quantum interference, it impacts all 2 to the n coefficients, leading to a new set of weighting factors on these aspects, alpha, beta, gamma, delta, et cetera. Now, we also have 2-qubit gates, or coupled qubit gates as they're called, of the type we just saw, like C0, where the state of 1 qubit impacts what happens to the 2nd qubit. But again, it's a single gate applied now to just 2 qubits, but it impacts 2 to the n coefficients through quantum interference, et cetera. And the goal of an algorithm designer is, by the end of the algorithm, to have put all of the weighting coefficient, all of the weighting into a single coefficient residing in front of one of these aspects. And that's because when we make a measurement, there's a massive collapse. And classically, we will only get one result out. And the probability that we get any one of these aspects goes as the magnitude squared of its weighting factor, or coefficient. This is called probability amplitude. And so the magnitude squared of the probability amplitude is the probability that, in this case, for example, we will measure qubit 1 in its 0 state, qubit 2 in its 0 state, and qubit 3 in the 1 state. And this encodes the answer to the question that we're trying to solve, or that this algorithm is trying to solve. And so the challenge for an algorithm designer is to come up with the right sequence of single and 2-qubit gates such that this happens, that all of the probability amplitude ideally resides in only one of these aspects, and it is the right answer to the problem we're trying to solve. Okay, so that's great. Why don't we have quantum computers today running algorithms at scale? And it turns out it's because of 2 time frames. One is coherence, and the other is the gate time. So the coherence time is the qubit's lifetime. You can take a quantum computer, put it into a single quantum superposition state. We'll call that psi, capital Psi. And let's say we can do that perfectly, or really, really well. But immediately from that time forward, the qubit is not just responding to the pulses we're applying to it, it's also responding to any electromagnetic disturbance in its environment. And what that means is that over time, this qubit state decays, blurs, and eventually is lost. Now, the qubits aren't gone, they're still there. But what happens is, as a function of time, starting with this perfect state psi, what I predict the state to be, given the operations that I'm performing, ends up deviating from the actual state of the qubit, because it's not just responding to my pulses, it's also responding to the environment. And so it ends up being in a different place than I expect. The time frame over which this happens is known as the qubit's coherence time, or lifetime. Now, the second time we care about is the gate time. How long does it take for us to implement one of these single qubit or 2-qubit gates? And take the one that takes the longest. That's a conservative estimate. And the figure of merit is, how many gates can I apply within the coherence time that I've got? And this is a proxy for a more rigorous metric called the gate fidelity, or the readout fidelity. Now, one point to make here is that long coherence times are not sufficient, right? It's the number of gates that you can implement before an error. And what I mean by this is that, look, you could imagine qubits built from, say, neutrinos. Neutrinos have basically an infinite coherence time. Why? Because they interact with essentially nothing, or they very rarely interact. So, on the surface of it, naively, you might think, well, it has a very, very long coherence time. Wouldn't it make a great qubit? But no, it wouldn't, because it's just as hard for us to implement gates on it. And so the number of gates per coherence time is not that great necessarily. It's very hard to control it. So it's the number of gates before an error that matters. And so based on this, we can make a comparison between different types of qubit modalities on different platforms. Now, these numbers are from 2019. I'll show the improvements that have been made since then. But on this vertical axis on the left is this proxy or figure of merit on the number of operations before an error. And you can see 1, 10, 100, 1,000, etc. That's basically one-to-one in what we would call the gate fidelity. So if you have one error in 100, that's 99% fidelity. One error in 1,000, that's 99.9% fidelity, etc. The horizontal axis is how rapidly I can implement my algorithm. So what is the gate speed? So 1 over the gate time is the gate speed and frequency. And of course, best performance is in the upper right corner. That's where we want to be. We want high fidelity gates, and we want to be able to implement them very rapidly. And so what you see are many different qubit modalities here and how they line up against one another for both single qubit and 2 qubit gates. And of course, you need both of these gates to do arbitrary quantum logic. So one of the leaders today is trapped ions, and here are a couple of my colleagues at MIT campus and Lincoln Laboratory who work on trapped ions. My own research is in superconducting qubits, along with some of my colleagues, and of course we have large teams that work with us at Lincoln Lab and at MIT campus. And if you ask us, what are we researching? Trapped ions are trying to make a higher fidelity 2 qubit gate. They're also trying to get faster. And superconducting qubits are already pretty fast. We're trying to get higher fidelity to get to this upper right corner, right? And so you can see we're both, in some sense, equally far away. Now, other qubit modalities that are up and coming, one is neutral atoms, which have made a lot of progress in the last couple of years. Here are some of my colleagues at MIT. And NV centers can be used, nitrogen vacancy centers in diamond can be used for quantum computing, and here's some of my colleagues at MIT and Lincoln working on it. But where they really shine is as magnetic field sensors, quantum sensing. And my own group, we're starting a silicon quantum dots effort here at MIT as well. And so there are many candidate technologies under development to realize the promise of quantum computing. As I mentioned, in the last couple of years, what's really changed is that the 2 qubit gate fidelities have got much better. So in fact, about a factor 10 better and faster as well. Okay, so with that, let me tell you a bit about superconducting qubits. That's my own research area. And we often call superconducting qubits artificial atoms. By analogy, of course, to the natural atoms that we have in our periodic table here. And one way to think of these is that the natural atoms, of course, are built from protons, neutrons, and electrons together in a Bohr-type model. And depending on the number of electrons, neutrons, and protons that you have different elements that have different properties. Okay, now superconducting qubits are circuits built from inductors, capacitors, and Josephson junctions. And depending on how you put them together, how many inductors, capacitors, junctions, and their values, you'll basically get something that has different properties, different circuits with different properties. The simplest one here you can think of as an LC circuit, a Josephson junction and a capacitor in parallel, and it forms basically a quantum circuit if you cool it down to low enough temperatures. We'll talk about that in a moment. But you can identify the lowest 2 levels as a 0 and a 1, and you go forward with this circuit. And again, by choosing different values and numbers of inductors, capacitors, and junctions, you can come up with different artificial atoms. This one here is the simplest one, called a fixed frequency transmon. It's basically the simplest one. It's our hydrogen atom, if you want to think of it that way. So superconducting qubits are artificial atoms whose properties we can design by choosing the values and numbers of these parameters. So let's dig into that a little bit. The simplest circuit that we can make that's quantum mechanical is an LC oscillator, an inductor and a capacitor in parallel. We think of this as a harmonic oscillator because the potential profile that it has is harmonic, CV squared or Li squared. You know, I or V, current or voltage, it's a square, whichever one you want to consider to be the potential energy, it goes as the square. And so we can think of voltage, or we can consider the phase, or reduced flux. And if we cool an LC oscillator down to cryogenic temperatures where the energy scale kT is much less than Planck's constant times the resonator frequency, 1 over square root of LC, then this is a quantum object. It will have discrete quantum energy levels, and we can associate 1 with 0, 1 with 1, 1 with 2, etc. But what we see is that the level separation between 0 and 1 and 1 and 2 and 2 and 3 are all the same. They are each h bar omega. This is a property of harmonic oscillators. So it's a quantum object, but it's not useful as a qubit yet, because if we try to drive the 0 to 1 transition, we'll end up driving also 1 to 2, 2 to 3, because each of these level transition is resonant with the field we're using to drive it. So we have to change something. And the thing that we choose to change and make nonlinear is the inductor. And that's because we have an object in superconducting systems called a Josephson junction, which takes two superconducting leads, in this case aluminum, let's say, and has a thin insulator, aluminum oxide, in between. And this is called a Josephson junction, named after Brian Josephson. And there's a voltage across the junction, a current through the junction. We're not going to talk too much about that, other than to say that Josephson identified the current and voltage relationship for this tunnel junction. And what we find is that if we combine them in the usual way to define an inductance, that this inductance is highly nonlinear in the current that's going through it. And so it is a nonlinear inductor. The inductance changes depending how much current is going through it. And in fact, the energy we can calculate by multiplying I times V and integrating over time. The energy goes as a cosine. So it is an anharmonic potential. So by making a circuit that has a Josephson junction inductance in parallel with a capacitance, we find that rather than a harmonic potential shown in the dashed red line, we actually get a cosine potential in the blue line. And the consequence of that is that the level transitions are no longer equal or degenerate. Because this is an anharmonic oscillator, level transitions have different energies. And so the 0-1 transition differs from the 1-2 or the 2-3 transition. And in fact, the degree to which they are different is called anharmonicity, and that's a property we can design for. The point is that now that we have a unique frequency, omega 0-1, we can uniquely derive the 0-1 transition without driving the 1-2 transition, right? So that's the advantage here. Okay, so there are many artificial atoms that can be built from this concept. As I said, this is just the simplest. This is our hydrogen atom, but with more junctions, more capacitors, more inductances, different values, we can actually make different artificial atoms with different properties. Now, we do have to cool them down, as I mentioned, and so we do that in a dilution refrigerator. And the reason is that we choose our qubit transition frequencies often to be around 5 gigahertz. Now, that's convenient because there are many electronics already developed with very high precision, good phase noise, et cetera, that we can use to drive these qubit transitions. But 5 gigahertz, if we think in terms of temperature, equate that to kT, h bar omega equals kT. What is the T? The temperature is 250 millikelvin. And we want to be much colder than that, because if you think of a Boltzmann factor, at 250 millikelvin, 5 gigahertz transitions will be driven just by thermal photons at 250 millikelvin, right? But if we're in a much colder environment, say 20 millikelvin, 10 times colder, we'll have very little or very few photons that can drive that transition, because you can think of the Arrhenius function. So the h bar omega divided by kt is in an exponent, so a factor 10 in the exponent has a very little likelihood to drive a transition 0 to 1. So we can reach 20 millikelvin or even a little bit colder in these refrigerators that we call dilution refrigerators. And this plate here, to give a scale size, is about 0.5 meter in diameter, 0.5 meter for this thermal finger, and all of that region will be at 20 millikelvin. Now, of course, it's inside a can, a nested layer of cans, actually, so that it can be under vacuum, et cetera. But we've taken the cans off so you can see the inside. And you can see packages that hold devices. You can see coax cables, microwave switches, isolators, attenuators, filters, et cetera. Some of them home built, some of them commercial. Through experience and trial and error, we know which ones will work cold. All of these are at 20 millikelvin and they operate. Now, we have these circuits, and of course, we fabricate or manufacture these circuits, and we do so using the same tool set that's used in a silicon foundry. And in fact, the wafers that we use here at MIT are silicon wafers. So this fabrication is completely compatible with silicon foundry. And as such, we have a lithographic scalability. We can lithographically print many of these qubits on a wafer. We fabricate on 200 millimeter wafers, that's shown here. Of course, we can do smaller sizes as well. And if we zoom in on one of these chips, you can see 5 plus signs. And this plus is actually the capacitor. So rather than a parallel plate capacitor, we use lateral capacitance. So the plus is one of the pads and the ground is the other pad. We have some resonators to the upper right, which we use to read out the qubits. And we have some control lines from the lower left, which we use to control the qubits. And so let's zoom in on one of these qubits. You can see this plus sign, capacitance to ground. It's capacitively coupled to a resonator. Turns out it's lambda over 4 resonator. And then you see one of these control lines coming in and just ending. So that's a charge line or voltage line, which we use to do high frequency control. It capacitively couples to this capacitor. And then here we have a flux line, which we use to bias this qubit. Now, if we zoom in further, we see that there is a loop here, and this loop has 2 junctions rather than 1. So this inductor is actually called a squid with 2 junctions forming a loop. And if we put a magnetic field through that loop, we're actually tuning the inductance. That means we're tuning the 0-1 transition frequency just by applying a current to an antenna that's nearby that threads magnetic field through the loop. Right. So that's a convenient feature, is we can make a tunable qubit, a qubit with a tunable 0-1 frequency, tunable by the magnetic field that we thread through the loop. We zoom in even further, we now have a single junction, and this is at the 200 nanometer scale or so. Okay, and we show up here that we can break the plane with a crossover or an air bridge like this, so we can jump over lines. We'll see at the end of the talk, true 3D integration. Now, how do we control these? We talked about an X gate before, but what does that mean? How do we apply a pulse to the X direction of a block sphere, right? And the way that we do that is through standard IQ mixing. So we have a local oscillator, which provides a frequency, a tone, continuous wave, that's close to, but not exactly resonant with our qubit 0-1 transition. And that goes into the LO port, local oscillator port of a mixer. We then have an arbitrary waveform generator that generates pulses with an envelope and at an intermediate frequency into the I or the Q port of our mixer. And we know that through standard IQ mixing, we'll get an output pulse that, if we use the I port, carries the same phase. The phase is unchanged, but we know that we get the local oscillator frequency plus or minus the intermediate frequency from the AWG. And through proper filtering or single sideband mixing, we can end up with just one of these sidebands. And that sideband itself will be resonant with the qubit. Now, we'll associate the I port with the X direction, which means that if we use instead the Q port, there's a 90-degree phase shift, right, in this frequency, or in this phase, sorry. And that will be along the Y direction, which is 90 degrees away from the X direction. 180 degrees, and now we're talking minus x, 270, we're talking minus y, and of course 360, we're back to the original 0. Now, what this is, of course, this pulse, we'll consider that as a source, goes into the fridge through some 50 ohm attenuators, and eventually to that terminated line, which is just terminated in an open, that capacitively couples to the capacitor of our qubit, and that's what drives the qubit transition. That's it. Okay, so let's take a look at what it looks like. So we've got this situation over here on the right, and what we have are some different pulses that we're applying. Now, I apologize for the color overload. The blue on the right here means in phase port. The red means quadrature port. And on the left here, the blue is the qubit and the red is the field that we're applying. So here we apply it to plus x. Here we apply it to minus x. And it's a pulse that does 180 degrees. Now we're going to switch to the q port, which is the y-axis. And now we have half the area, so we only rotate half as far, and that's a pi/2 pulse. So let's take a look at it again. So we've got plus x, which does 180 degree rotation. Now minus x, which is minus 180 degree rotation. Now we'll switch to the q port, or the y-axis, 180 degrees. And now pi/2, 90 degrees, brings us up to the equator, and another pi/2 will bring us back to the North Pole. So again, in phase, we associate with the x-axis. Quadrature, we associate with the y-axis. And this is how we do IQ pulsing with microwaves. So the last thing I'll say is that superconducting qubits over the last 20, 25 years have improved more than 5 orders of magnitude in their coherence times. That's one of the reasons that they're a leader today. You can find this plot here, which is going from the first qubit back in 1999 with around a nanosecond coherence up to the qubits today, which are approaching a millisecond. And you can find this in some of our review papers, which I show here. I would get the archive versions. You can get those. This MRS bulletin is the other one on material science from 2013. Here are some typical numbers for T2, which is the coherence time, the lifetime on the equator. So some flux qubits at 100 microsecond, 2D transmons, hundreds of microseconds now, even we've seen as high as 500 microseconds. 3D transmons, we're not really doing those anymore. That's a qubit that's stuck inside a large 3D resonator, but at 2014, we had 150 microseconds. We have fluxonium now that's got a T2 of around 350 microseconds. So these improvements in coherence have been made by groups worldwide, and they result from improvements to materials, fabrication, and design, a combination of all three, incremental steps. Okay, and if you ask what the fidelities are today, our single qubit fidelities are greater than what we will say 3 nines or 99.9%. And the way we do this is through something called randomized benchmarking, which is that we throw a series of random gates, which we know but are selected at random from these different gates that you see here. And then we look at the decay function. Of course, the more gates we apply, the more likely we are to have an error on average. And we just look at what we actually measure versus what we expect from that series of random gates. And we then increase the number of gates. These gates are called Clifford gates. We'll then interleave between those random gates the gate that we are trying to assess, for example, x pi. So we have random gate x pi, random gate x pi, random gate x pi, and we keep doing that. And we look at how much did the error rate increase. And that increase in error rate must be due to the interleaved gate x pi. And so that's how we infer the error for a single gate. And you can see here, all of these are above 3 nines. With fluxonium, we now have 4 nines fidelities. For 2 qubit gates, it's the same story. We do randomized benchmarking, and we get gate fidelities that exceed 99.5%. So here we're almost at 3 nines for the I swap gate. For the control Z, we're about 99.8%. And I'll say that with fluxonium 2 qubit gates, we've now exceeded 99.9%. That paper will appear on the archive, or it has appeared on the archive, hopefully in publication soon. So this is what quantum computers look like today. Here's a quantum computer from IBM. I believe this is the Eagle processor with 127 qubits. They now have a 400 plus qubit version. This is Google's Sycamore processor, 53 qubits. They now have a larger version, which I think has 72 qubits on it. This is Rigetti, one of Rigetti's qubits. This is an older one, I think has 20 or 30 qubits on it. These are all superconducting qubits. This one, IonQ, inside this black box is optics that controls and holds trapped ions, traps the ions. This is D-Wave's computer, which is also based on superconductivity. There's a different type of computing rather than the gate model that we talked about today. This is called a quantum annealer, which seeks the ground state of some complicated potential. This, of course, is not a quantum computer. You'll recognize this as the Wright Flyer. And I put this picture here because I believe that that's about the stage we're at with quantum computing today, which is pretty fantastic. You know, when the Wright Flyer actually took off and flew, it didn't fly very high. You can see it's not even 6 feet off the ground. It only flew for about 100 feet or so. You can see he's laying down, doesn't even have a seat, doesn't even have a fuselage. So if it really did go high, it'd be quite cold. But we know that when we saw this, we could tell that, okay, commercial aviation will come. It's still a couple decades away, but we know that commercial aviation is possible. And I believe with these quantum computers and the demonstrations that we've seen to date, we know that commercial viable quantum computers will come, but it's still a ways off. And we know that there's promise, but to realize that promise, we need to engineer quantum systems that are robust, reproducible, and extensible. Just like with the Wright Flyer, we knew that we needed to make airplanes that were robust, reproducible, safe, and extensible. Okay, so let's talk a little bit about that. How do we engineer quantum systems? Well, if you want to engineer a quantum system, of course, you need an architecture. And this one is due to Cody Jones. He's currently at Google, but when he wrote this paper, he was at Stanford University with Yoshi Yamamoto, my own PhD advisor, and Cody's as well. And the layers that you see here start at the bottom, say with the physical qubit layers, say superconducting qubits laid out on a chip. At the top, you have the application layer, which is basically the human-computer interface, a terminal, which is a classical computer, where we program the quantum algorithm. Which gates do we need to apply? And that, of course, is interpreted by a logical controller, that's layer 4 here, which compiles those gates, uses the electronics to generate them, and it's going to apply them to the physical qubits. Now, those are the algorithmic gates. Now, there's 2 other layers which also involve gates, and those are layer 2, which is passive error suppression. These are gates that we apply simply to reduce the rate of errors occurring. This is open loop, if you want to think of it that way, error cancellation techniques, where we just throw gates at the qubits because we know it's good to do. We'll see an example in a moment. Layer 3 is active quantum error correction. This is where we look at a syndrome or an indicator that tells us an error occurred somewhere in the system. It also tells us the type of error and where it occurred. And what the logical controller needs to do on every clock cycle is, of course, implement the algorithm step by step, implement the passive error suppression, but also look at these syndromes or these indicators that are coming out. These are different than the data qubits. Keep track of the errors, and occasionally you're going to have to go in and fix those errors at certain points of the algorithm. This has to happen on every clock cycle. So I like to think of this layers 1, 2, and 3 in the context of lacrosse to give a physical intuition. And if you're familiar with lacrosse, you have a stick with a basket at the end, and you want to hold a ball in that basket, run down the field, throw it in your opponent's goal without losing the ball. Okay. So for physical qubits are noisy, their environment is noisy, and their control is noisy. And so what this is represented by is this person here who wasn't very happy to give this demonstration because this is not how you play lacrosse, but it's analogous to physical qubits. So he's going to hold the ball in his basket and then run across the ground. And the ground, of course, is uneven. And of course, his running or control is also noisy. And of course, the ball just falls out very quickly, due both to his running and the noise, but also to the fact that the ground itself is not completely smooth. So these are physical qubits as they are. So of course, that's not how you play lacrosse. The way you play lacrosse is with passive error suppression. What you do is you cradle the ball back and forth. You do a 180-degree rotation, right, of the basket. You don't think about it. You just do it all the time because you know that this decouples the noise of your running and the noise of your holding the ball, so that the ball stays in the basket, and then you can go down and score a goal, right? So this cradling in lacrosse is active error suppression, which decouples the noise of the ground and of the running from the ball and keeps the ball in the basket, protects the information, so to speak. Now, even if you do this passive error suppression called cradling, you can still have errors, right? And those errors occur because the defender or decoherence comes up behind you, the big D, knocks the ball out. You can't help that. It's going to happen. When that happens, two things need to occur. First, you need to identify that the ball fell out. You need to identify an error occurred. And then you actively need to go over and pick it up, right? So that's what this player is doing right now. He identified the error occurred, picked it up. What does he do? He immediately starts passive error suppression all over again. Okay, this is what happens in a quantum computer on each and every clock cycle. Okay. So with that, in the last few slides, I'd just like to talk briefly about some 3D integration activities that are going to allow us to scale to larger sizes. So in my own group here, we're currently working with arrays of 16 qubits. So that's a 4x4 array. The blue indicates the capacitor, as I mentioned before. We looked before at a one-dimensional line of these. And this, in fact, is the fluxonium device that I mentioned earlier that has a single qubit fidelities of 4 nines and 2 qubit fidelities more than 3 nines. But of course, we don't want to do just 2 qubits, and we don't want to do just 5 qubits in a line. We want to do 2D arrays of qubits. But what you can see here is that it's getting quite crowded with all the lines that we need to bring in to control these qubits. And so we know that we need to 3D integrate. And in fact, with this device, we have 3D integrated. Where you see these black lines, that's actually open field. And the resonator itself is on another plane through flip chip. But what you can think of is in the future, we want to have not just 2 chips, but 3 chips. And what we call is a 3-stack. This qubit chip is the one that's on top, and it's flipped face down. And there are some capacitors here, and I've illustrated just an illustration only of the electric field lines that go from one plate to the other. And the way that we do this is with high resistivity silicon for the qubit chip, and then high resistivity silicon for this interposer chip, as we call it. And the interposer is made with the same silicon, high resistivity, high Q. And what that means is that even though we flip chip the qubit over, basically it's seeing the same environment. So its coherence times probably won't go down, and they don't go down very much at all. Now, by having another surface here on the interposer, this allows us some flexibility where we can have other elements like the resonators that would go here, or control lines, or even active couplers that would couple neighboring qubits together. Now, in addition to that, we want to have in this interposer, we want to have through silicon vias that go all the way through the silicon that can carry signals up to the qubit. And these are superconducting through silicon vias. And at the bottom, we have what you might think of as a multi-chip module or a readout and interconnect IC, or ROIC, where there are multiple wiring layers that allow us to route signals, say from the edge of a package, route signals to underneath the qubit that we want to address, and then the through silicon via brings up the signal to the qubit, addresses it, and then readout brings the signal back down, and we can take it out to the edge of our package and up out of the fridge. So this is called the 3-stack, and the top chip is the qubit chip. The middle chip is the interposer, and what we see here is a side image, side cut SEM image of the through silicon vias. They're 200 microns thick, so we've thinned the wafer down to 200 microns. The via itself is lined with titanium nitride, which is a superconductor. And this material superconducts at about 2.5 Kelvin. Turns out aluminum superconducts around 1 Kelvin, and our dilution refrigerator is, 10 millikelvin, so it's 100 times colder, so well below the transition temperature. Now, the feature of a superconductor, I didn't mention it, is that it has no resistance below a certain temperature called the transition temperature. And here you can see that we have 1,600 of these vias in series. We also have 3,200 in series. And above the transition temperature, of course, tinitride above the transition temperature has resistance. And you can see that the resistance doubles when we have twice as many vias. But below the transition temperature, it superconducts, right? And so both of these, whether 3,200 or 1,600 vias in series, both have zero resistance, true zero resistance. Now, this lower readout and interconnect layer, if we took a side cut of that SEM image, you can see that it's got many metal layers. Metals is layer 0, 1, 2, all the way up through 7, so 8 metal layers. There are vias that connect the layers together. Turns out it also has resistors, active Josephson junctions, and even pads. Now, this is not, we used to make qubits out of these, but basically today we're just thinking of using this as the readout and interconnect layer where we can route signals wherever they need to go. Think of a complicated highway system of roads going over and under each other till you get to where you need to go, and then the TSV will take you up to the qubit. With junctions here, though, we can imagine in the future having or co-locating some of our electronics, digital logic, based on superconductors called SFQ, single flux quantum logic. Won't go into that, but that becomes possible here, as well as traveling wave parametric amplifiers that we can use to amplify the signal. These are based on, 2, 3, 4,000 Josephson junctions in series. High gain, 20, 25 dB, but very, very low loss. In fact, approaching even the quantum limit. And so with that, let me conclude. I'd like to acknowledge my colleagues at MIT Lincoln Laboratory, as well as at the MIT campus in the Engineering Quantum Systems group. Of course, many, many people contributed to the work that I showed you here today. And also want to acknowledge our many sponsors who helped fund this work and made it all possible. And I'd like to thank you for your attention.